the whole slide. Oops, sorry. Okay, so these are getting more and more competitive. So you see here the ionic conductivity of room temperatures, 10 to the negative 6 millisiemens per centimeter to 1 millisiemens per centimeter. So you can see we're getting pretty competitive to the liquid electrolytes at room temperature. We're aiming for, around 10 millisiemens per centimeter to be competitive. But what you see here is, oh, sorry, I said room temperature. I meant to say 300 C. So this is elevated temperature. You have to increase the operational temperature to 300, but we're getting there, right? And you have to start somewhere, and you're not just going to magically find, this compound. So people have studied these type of compounds to understand, well, what is it? How do we engineer high ion conductivity? How do we isolate variables like atomic disorder? Does that help the lithium ions migrate? What about opening that bottleneck that we're talking about, replacing with larger anion, or create allele-valence substitution so that there's chemical disorder? So people play around with this, with a systematic chemical reasoning to then get to this particular composition. You see a mixture of zinc, a mixture of germanium, and they all sit on this M site. Okay, so here you have your PO4, so that's in the purple, and so if you start to substitute out phosphorus and put in germanium, then you create atomic disorder for these lithium ions to start migrating, and you increase the ion conductivity. Now it's 6 millisiemens per centimeter at 200 C. So you can do more. So once you have something like this, you have, let's say, a starting compound still in the same family, Li3XO4. What is X? X can be phosphorus, X can be vanadium, X can be arsenic. Okay. Typically, arsenic is not used just because of its toxicity, but it can sit on those sites. So that's X, and then you have your M, so that can be silicon, germanium, titanium. You mix these two, and interestingly, when you measure the ionic conductivity, the N members are not the ones with high ionic conductivity. It's the solid solution in the middle that has high ionic conductivity, and that has to do with atomic disorder that you created by mixing these elements together on one site. And so that increases, so cation co-substitution will increase your ionic conductivity. Okay. Then there's also, you can mix, different elements, but you can mix what's called allele-valence substitution. So you mix different oxidation states together. So you can put in trivalent, so 3+ cation. You can also put in divalent, so 2+ cation. And this competition between the oxidation states will also create vacancies for charge neutrality. So if you put something in that's 2+ on a site that was at 1.3+, right? Then you need some vacancy to compensate for that, or another 1+. So just by the sheer, substitution, playing around and making solid solutions, you create atomic disorder, which is the name of the game. You increase ion conductivity. So that's a general good first guiding principle on how to increase ion conductivity from the crystallographic point of view, atomic point of view. Then we move on to what's called kinasicon. This is based after sodium containing compounds, but the lithium. So the term is historic. Initially there's no sodium if you're working on lithium ion solid electrolytes. So their general recipe is you have some alkali metal, lithium in our case to begin with, and then you have some metal, and then you have another metal, so metal M prime to distinguish from M, then you have a phosphate. So if the two M's are the same, then you have M2. If they're different, then it's M prime. So what is M? What can you put on the M side? You can put anything that is trivalent, so 3+ transition metal. Okay. The M prime needs to be a 4+ oxidation state. That's also a transition metal. So what have people looked at? People looked at things like putting in aluminum, gallium, chromium, scandium, yttrium, iron, lanthanum, titanium, germanium. And when you put it all together, you get this general composition. And these are the two compounds that have emerged as either electrochemically stable, air stable. That's quite attractive from a manufacturing point of view. Right? Some of the sulfides that we talked about one lecture ago were the sulfide compounds. Those are great in terms of performance metrics of high ion conductivity, but manufacturing sulfides has its own challenges, which are not insurmountable if that is your aim in life. Right? If you want to make the highest ionic conductor, then you go out and make a sulfide, right? You overcome the manufacturing challenges, right? I mean, just like Intel overcomes clean room challenges, and everybody dresses up in a bunny suit, and everybody goes into the workplace, and it's like 1,000 dust particles, per room. You've overcome the challenges to make your device work. So that's that. And the syntheses of these phosphate-based, either titanium containing or germanium containing LATP is a common acronym, LAGP. So you'll see this a lot in the literature. People try to really make this work. The ionic connectivities are okay, right? So they're 10 to the -2 millisiemens per centimeter, which is low-ish, right? We're aiming for 10 here, 10 millisiemens per centimeter. There's a lot of the pathways for ionic diffusion are many, but when you look at a crystal structure like this and you think, before I do any experiment, can I predict if this compound is even worth going into the lab and making a battery cell, hooking up the electrodes and testing it? You can predict that beforehand if you just look at the crystal structure and you say, well, what are the diffusive pathways? How do the lithium ions migrate? And is there an energy, is the energy landscape low enough so that this is a competitive compound for me to spend time in the lab? So we now know enough, we have a body of literature that we tabulated where we have a good sense of, if you know the crystal structure, you can actually predict how the material is going to perform optimally. So real life is suboptimal, right? You have a crystal structure, you know how the ions are going to migrate. But when you go into the lab, what you find is if you have an oxide, you're going to have to sinter it, right? You're going to have electrode electrolyte contact issues. So starting out, okay, the crystal structure is ideal, but once you make that actual compound, you're working with the powder, that's when all the engineering challenges come up. That's when you call your mechanical engineering friend and you say, let's work together, because, it's the bigger challenge. Yes, Alex.
So bottleneck size is not the only determining factor for increasing ionic conductivity. The other only factor would be migration pathway or migration resistance.
Well, migration resistance, yes, but they're interconnected, right? You can open up the bottleneck, but by introducing a different element, and by doing so, you've also introduced atomic disorders, unless you replace all of the ions. So unless you replace all of the oxide, all of the oxygen ion with sulfide, by having a mixture on the anion side, you've also introduced not cation disorder, but now anionic disorder, which is another strategy for increasing ionic conductivity. So this is a review paper that I've referred to a lot because all of these co-authors have done a lot of work on trying to understand and isolate all these variables so that we can pinpoint, based on the crystal structure, which will be the determining factor. Now we switch over to the sulfide. So we have the lisicons, the lithium superionic conductor class of compounds, family of compounds. Now we have thiolisicon. So basically, you take in the oxide, you take out the oxygen, you replace it with sulfur. So instead of NO4, you now have NS4. Okay, so the thiol is sulfur containing. So that's all it means. It's the same crystal structure, but so it's isostructural, but you're taking the oxygen out, put in the sulfur. And so this is the compound that has excited more recent work on sulfide-based solid electrolytes. Interestingly, what happens is if you make this compound, you get the low temperature gamma phase. This phase, you can see ion conductivity room temperature is 10 to the minus 4, nowhere near 10, right? But that doesn't mean we stop all fundamental studies and say, we don't care. Because what we can study and learn from the system is when you phase transform to this beta phase, the ion conductivity increases by basically 2x, right? Going from 3 to 8, it's still 10 to the minus 4 millisiemens per centimeter. But what we've learned is if you can control how the lithium substructure looks like, so you can see all these tetrahedra point in the same direction. When you phase transform to this beta phase, you see now they zigzag, right? The same thing happens with the anionic framework. Here, they're all the tetrahedra are pointing this way. In the beta phase, they're also zigzagging. So the apex of each polyhedron or tetrahedron are pointing 180 degrees from each other or in opposite direction. And then this even higher temperature alpha phase, we don't know. Yeah. To be seen. But what that's telling us is if you can create this sort of polyhedral disorder, you can increase ion conductivity. So then you go back to your 230 space groups, 200,000 compounds in the inorganic crystal structure database, and you say, okay, well, can I find substructures within different families of compounds that have something like this, where it just increase the temperature, trap this phase somehow by different synthetic methods, and then get to a higher ion conductivity phase. So basically, you're saying, can I revisit all the compounds that I dismissed before because I thought they were going to be low ion conductivity, and find a way to synthesize and stabilize high temperature phases at lower temperature to then increase ion conductivity that way? The answer is yes. The answer is you can form what's called nanoporous beta lithium biophosphate. And this is the work out of Oak Ridge National Lab, actually quite a number of years ago now, 8 years. And what they find is if you have just this like bulk compound, even in the the high ion conductivity phase, here's the ion conductivity, they get it up to 10 to the minus 4 Siemens per centimeter, so that's 0.1 ish order of magnitude millisiemens per centimeter. But if you make it amorphous, now you've increased the ion conductivity quite a bit. So not only can you change and stabilize the crystal structure, so what was once the high temperature phase at the nanoscale, you stabilize it, but on top of that, you can make it amorphous and porous, and you can engineer, so you change the morphology in addition to the phase, and you can increase ion conductivity that way as well. Okay. So this is a really lovely Journal of American Chemical Society paper. I have listed here other compounds that you may see in the literature in your perusing of solid electrolyte, and the different classes of the different compounds like lithium germanium sulfide, lithium tin sulfide, and also solid solutions of these will increase ion conductivity the same way. You make a solid solution, and the compounds that are in the middle with the compositions that are in the middle, the two end members will have a higher ion conductivity. The diffusion pathway is really interesting because with certain compositions, as you see here, it's 1D, as in like there's a preferred pathway of high ion conductivity, and then in the two other directions, they're not as fast. ideally you want high diffusion, right, in all directions. So there are some limitations to these type of compounds, because if you have 1D or 2D, you know, you're going to be limited by how you orient your powders. Okay. And then, so this is thiolisocon, but it deserves its own slide because it is the reigning ionic conductor. It's been reported that in one direction it has 27 millisieverts per centimeter, in another direction 7, but on average it's about 12. So this in 2011, when this paper came out, that really excited everybody because now you have an intrinsically high ionic conductor. So even though it starts off at 12, even if it's slightly porous, maybe it's not as you haven't sintered it, it doesn't have theoretical density, it hasn't achieved even 100% theoretical density. You've already started with something that beats 1 molar LiPF6 in ethylene carbonate, dimethyl carbonate. So that's PS5X. It's named after this original compound, the Greek name, Electrolytes. And so this is a halide. You have chloride, you have bromide, you have iodide, you can induce high ion conductivity. What's also exciting about some of these compounds is that they're air stable, and you can make them via a number of ways. Solid state, so you mix them with powder, solution state, and ball mill. But their performance is really dependent on the thermal treatment during synthesis and also on cooling. So anyway, very exciting. And I believe that wraps up this lecture. The one thing I want to end on is electrochemical stability. We talked about how the voltage window does matter. So you can see here, here's LGPS, high ion conductivity, but here's LGPS. But if you look at the electrochemical window, it's about stable around 2 volts. From the cathode discussion that we're looking at, cathodes that can perform at 4, maybe even 5, 4.7 volts versus lithium. And if you want to work against, anodes, that's 0. So if you want to work against a lithium metal anode, you have a compound that operates here and here, and your electrolyte is now stable here. So will your battery run? Third question. Yes. But what do you think is going to make this battery run? Even though the electrochemical stability window is very narrow, it does not span the entire voltage window that you want it to span. Does anyone recall the 3-letter word, 3-letter acronym? Starts with an S. Yes, Dagny. Yes, other stuff. All this other stuff is called the solid electrolyte interface. Interface at the interface with the C. Yes, the SEI is what will save you. It will make your battery run. But what in the world is the SEI at the solid electrolyte interface? Those are ongoing studies. There you go. Okay. Now, all right, team. We're going to switch gears and go over to the proposal. All right, the proposal. And who has had time to read the proposal? The template anyway, the guidelines.
I looked over it somewhat.
Okay.
and It tells me a lot, but it doesn't
Mhm.
tell me what exactly we're supposed to actually do, like design. It just
Yeah,
like
so it's really a research project. You know, we want you to assess an energy technology. There it is. So that's basically it. Now, there are going to be some guidelines. So, but probably first you're interested in the due dates. Okay.